Hi, this video is a part of exploratory data analysis using Python playlist. In this video, I'll be talking about data wrangling, exploratory data analysis, model development, model evaluation, and refinement finally for the automobile dataset. So we'll begin with identifying and handling the missing values, then we'll do data standardization, and we'll look at the data normalization. Finally, then we will do binning and we'll create some indicator and dummy variables in data wrangling part. In exploratory data analysis part, we'll look at the potential predictor variables that could be used for model development, and then we'll look at some descriptive statistics, and we'll do some groups analysis using group by method, and we will look at this correlation and causation problem, and we'll look at those ANOVA scores and those analysis of variance, and finally we will conclude this EDA part. So this data wrangling and exploratory data analysis part once done, then we will focus on model development, evaluation, and refinement, where we'll be looking at multiple linear regression, polynomial regression, random forest, and then we'll refine those models using scikit-learn. So let's jump to the notebook to understand it in a better way. So we'll begin with data wrangling, then exploratory data analysis, then model development, evaluation, and refinement. We import all the necessary libraries, then load the dataset having these names for columns, and this is the website from which we could receive our data, from which we could download our data. So the data in that website is in comma separated files, so we use this read_csv method, and this is the file name, and these are the name of the columns. So we have total 205 rows, 205 automobile samples, and 26 columns. So these 26 are different features. So if you look at it, we have some features containing this question mark, and this question mark actually represents the missing values for this feature for specific automobile, for specific sample. Okay, then what we could do is, first of all, we could convert this question mark to NaN. NaN is actually used in NumPy for not a number, so this is used for various methods where we want to replace these NaN values, these missing values, with something logical, with something which I'll be explaining. So the first thing is that we want to replace this question mark with numpy.nan. After that, you look at after doing that, we have converted this question mark into this NaN. Then we want to know the missing values, where these missing values basically occur. So this is null method for this data frame will return the true and false for each of the element containing null value, containing this NaN value or not. So this null value or NaN value, not a number, or missing value, all of these represent the same thing. So once we have this, then what we will do is, this true means 1, this false means 0. We will sum all of the values. Once we sum it, then we can find out the total number of null values in different columns. So for example, this column normalizing losses contain 41 null values or NaN values, and the same goes for this stroke column containing 4 null values or NaN values. What we will be doing is that we will be handling them. We could either drop data completely, drop the whole row or the whole column containing null values or NaN values, but the data is sometimes very costly. So for that reason, we don't want to lose information. We don't want to lose either whole column or whole row, because with dropping these missing values, if we drop the whole row or column, we are also dropping other values, other valuable information. So instead, we want to come up with something more efficient. So one way is to replace the null values by the mean of that column. So consider these 5 different columns, and we want to replace their NaN values with the average of all other present values. So for each of the column, what we will do is, we will first of all convert its type to float. So then we want to find out the mean. That is what we get, the average or mean. And once we have that average or mean, we will replace these numpy.nan values, that those null values, with the average. And in place is equal to true means that this data frames has this change. It will not create a new copy. Instead, the change, what is the change? The change is replacing this NaN with these average values. This change will happen, and that is why we set this argument in place is equal to true. The next part is that we want to calculate total number of NaN values for this number of doors column. Why? Because we want to replace NaN values in this column by the most frequent class. So I have already explained this value counts. What it does is basically, first of all, it look at the number of unique values in the specific column, and then group by that column, group by the whole data by that columns having some unique number of values, and then calculate the number of counts in each of that unique value. So we are having these 2 unique values for number of doors. So So we are having the automobiles containing 4 number of doors or 2 number of doors. So as we have seen here, there are more cars with 4 number of doors instead of 2. So for that reason, we will replace this numpy.nan with 4. And the trick of extracting out the class having maximum number of instances, for example, these terminologies should not be confused with the object-oriented programming concepts. So here, this class, by class I mean the type, actually the class of the column, the different unique values of the column. So we have 2 unique values, so I'm calling both of them a class. So this is one class of value for this column number of doors, and this is another class of value for this column number of doors. So this value 4 can be extracted out by applying this function idxmax. So this is like finding out the index of that class having maximum number of counts, and in this case we are having this 4. So if you want to automate it, this function will really help us out. So once we have extracted it, we could use that to replace our values. Finally, we will drop the entire rows for some of the cases. Consider this price column. So in this price column, what we want to do is we want to this deletion of complete rows containing nan values in this price column. So wherever there is price column, we will drop that value. So this is drop na method which we have used here. And once we have dropped those values, so of course the index, we have removed some values, and those values indexes has also been removed. So for that reason we reset the index. Once you have resetted the index, then we look at the data types of each of the column, and we look at some of the columns containing data type which does not make sense. For example, this bore and stroke, these are values, and if we look at their data type, it's object, it's string. However, it should be float. So for that reason we convert its data type to float. And then for normalized losses, we convert its data type to integer, and for price we convert its data type to float, and then peak RPM is also converted to float. So once we have converted all the data types, now it makes sense why it was not float in the first place. Maybe the value float, it was stored as a string. It is also possible. So in the data collection process, this sometimes happens. So for that reason, this function of data types is really helpful to know or values of data and whether it logically makes sense or not. Now let's come to this data standardization part. Consider we have stored our data in miles per gallon, but for some country that we are developing this application, there the data is in liter per 100 kilometers. So we have to convert these values. So this is the formula for conversion, and we do it for all the columns containing this information of miles per gallon, so containing this unit of information. So we convert this unit into another unit. This is what we call standardizing the data. And normalization basically means that we want the range of values between some specific values. So in this case, we want the range of values between 0 to 1. For that reason, we actually divide the length, width, and height by their maximum values. So this is what we get finally, a value between 0 to 1. And then we do the binning. Binning is the process of placing a specific kind of data set having specific characteristic in a single category. Consider we are having this horsepower column for each of the car, and this horsepower is actually a numerical value, but we can categorize different cars based on their horsepower. So we can have this low horsepower car and medium horsepower cars and high horsepower cars depending on the value of the horsepower. So we could create this range. So consider we want to create these 3 bins, low, medium, and high. For that reason, what we will do is we'll look at their range of horsepowers and we'll divide it by 4. Once we divide it by 4, we get this value 53.5. So it means that we will be creating values from minimum to maximum horsepower by this single value bin width separation. So the minimum horsepower is 48 for any car in our data set, and we will add this bin width of 53.5, and then we'll again add this bin width of 53.5, and we'll again add this bin width of 53.5, and this is what our maximum horsepower for any car in our data is. So based on these 4 values, what we will do is we will cut our data set using these bins, and these bins are actually these 4 values. So what will happen based on that is given any value, consider this single car having this horsepower of 111. So this 111 is in between second range 101.5 and 155. So for this second range we have the name medium. So for that reason we have the group names for each of the group that car belongs to. So then what we will do is we will just create a new column which we will call horsepower bin. So for each of the value of horsepower we have created a new column containing its associated group, containing its association with it. So if it's horsepower 111, then we'll say that it's a medium horsepower car, and if it's 101 then it's low horsepower car. If it's 48, of course it's low. It's 182, it means it's high horsepower car. So this is how we do the binning. Once we have done the binning, we will visualize these bins, and this is basically visualization part. So we have total number of 3 categories. We'll create this histogram, and once we have created this histogram, then this is basically a part of creating the color for each of this patch. So each of this bin, each of this what we call this single column in the histogram, in each of this histogram. Once we have done that, then we set the title, Y label and X label, and finally this part, these 3 parts, m patches dot patch, is actually creating these patches, this which is kind of representing the legend. So this legend is created using this m patches dot patch. If you're confused in this data visualization part, I have already created the videos, the playlist data visualization using Python, in which I have explained different visualization and these patches in detail in one of the video. Okay, just have a look at that data visualization part. You will be in better place to understand all of this X and figure and all of these patches and all of these things. I hope so. Okay, then we will create these indicator variables or dummy variables. First of all, these are the total number of columns that we have, and these are the names. And then we will look at this fuel type, and this fuel type, if you look at it, so it's gas or diesel. So given this gas or diesel, we want to convert it into a numerical value, because in model development and machine learning that we will be applying afterwards, needs in input in integer or in float or in, I mean, a numerical value is important for a lot of machine learning algorithms. So that's why what we will do is we'll use this get dummies function, this get dummies method of pandas. What it will do is it will create a one hot encoding for all of this column. So this diesel will be created as a new column containing zeros in all the places where there is gas and 1 in place where there is diesel. So this is the place 199 sample, and 199 sample contains this one, and gas will contain 1 in all the places where diesel does not exist, and will contain 0 at a place where diesel does exist. So this is what we call one hot encoding, and this is what we also call getting dummies. Okay, then once we have this dummy, then we will actually change the name into a logical name from gas to fuel type gas and diesel to fuel type diesel. So once this is done, then we will concatenate this data frame that we have created, a new data frame containing these 2 columns, into our base data set. And once we have done that, this is how it looks. These 2 columns, these 2 new columns have been added. Okay, then what we will do is we will also drop this fuel type, because this fuel type has been converted and added in the form of numerical values. Okay, then we will repeat the same steps for this aspiration column. Okay, once we have done that, then the clean data set will be stored in the data frame. Till now we have completely completed this cleaning part of this data frame. This clean data frame can be used directly in machine learning model, which we will be using, and can be used for exploratory data analysis or any other purpose. So let's look at this exploratory data analysis part, where we look at these different data types. And once we have those data types, we will be looking look at these data types, and they will make sense. If they make sense, it's okay. If they don't, so we convert the type of the columns. So once done, then we look at the first thing that we will look at is the correlation. So this is done to find out the potential predictor variable. We want to predict the price of the car. So this is what we want to predict, the price. So we will find out the correlation of each of the column or each of the variable with itself and with all of the other variables. So in this way, once we have done that, then we will look at engine size. Once done, then we look at this engine size variable, highway miles per gallon variable, peak RPM variable, and the stroke variable, and their correlation with the price. So of course the price correlation with itself is completely 1, and with engine size it's good correlation of 0.87, and with highway miles per gallon it's negative. Of course, if a car is having greater highway miles per gallon, it must have lower price because it's efficient. So the engine size, the greater the engine size, the greater the price. It makes sense. And peak RPM is having less of an impact on the price, but still it has some impact, some negative impact. And then stroke seems to be having the least impact in out of these 4 variables. Okay, once we have done that, so we can conclude that engine size has strong linear relationship, and then then this highway MPG is having a strong negative relationship. We can visualize these linear relationships and these different relationships using these models. So this is how we could use this C-Bon library, and we have also covered in the data visualization using Python playlist, adding these multiple plots in this single figure. And how do we do this? Create this linear plot using SNS. So this is regression. This is what we call regression plots. This is like setting title for each of the subplot. And it's really easy. We just give the X value and the Y value and the data frame. So these are the name of the columns, and this is the data frame that we do, and this is the color that we want, and this is the marker for the points, scatter points that we want. Okay, then these are just properties of scatter points. The size of scatter point is 50 in this case, and this is the subplot where we want to plot this stroke and price. So in this case it's x3, so this is x3. Okay, once done, then we also look at the box plot. Box plots are basically used where we have categorical variables. So consider this body style column. So we have these 5 different types of body styles for all the cars. So it may be convertible, hatchback, and these wagon, and these different data type, these different car types. So given these car types, once we have created these box plots, so this box plot is kind of giving us this distribution for each of this body style. If we look at these distribution, they have a lot of overlap. So it means that it's not a very good predictor. It could not be a good predictor because the separation of distributions will be difficult given this column, this feature as a predictor. And in opposition to that, in contrast to that, we have this another categorical variable or feature, engine location. So this has a very strong prediction on the price. So if you look at the box plot for this front engine located cars and rear or back engine located cars, then we could find a significant difference of these distributions. So this significant difference in the distribution for price prediction makes this engine location a very good predictor for price. So it should be used for machine learning algorithm. So once we have done that, then we look at this drive wheels, and we find the significant difference in the distribution even here. So the price for price prediction, this drive wheels could also be a good predictor. Okay, once we have done that, then we look at this descriptive statistics. We describe with this describe method, we can find out all the descriptive statistics from count, mean, standard deviation, minimum 25%, 50%, and 75% quartiles, and then maximum for each of the numerical variable. So this is what we could find. So once we have found that, it needs a lot of time to find it needs a lot of understanding to extract something out of directly from this describe function. However, it's good to have this function understanding, because sometimes for comparison it's really cool to find out the mean values, the difference in the mean values, and the standard deviation. So greater the standard deviation means greater the variance in these values. So there are a lot of scattering in that feature. So that could be a possible feature for further analysis, because if there are a lot of variations, so it means it contains a lot of information. Now that is the part of a data analyst to find out whether it's nice or there is something internal, or how could we separate out and how could we engineer new features from such kind of different features to have something at the end, to have some features at the end which are more separable and which are more easily learned by the machine learning algorithms. So this is domain specific thing, but the understanding that we could find out and we could compare these mean and standard deviation and all of these values are really great. One more thing is that all of these values, this descriptive statistics is just for numerical values. However, we could also do this descriptive statistics for all the objects. So for objects, we have number of counts, number of unique items, and the most top item and the most frequent item. So these are some of the things that we could do with the categorical variables, or the variables having the data type object. Okay, then let's begin with this drive wheels. As I've already explained here, that drive wheels could be a good predictor. So let's dive deep here, and we could find out the value counts. And the value counts is basically the total number of counts for each of the unique value in the drive wheels column. So we have total number of 118 cars with drive wheels FWD, which is forward, and this is 75 with backward, and four wheelers are actually 8. So then we can repeat these above steps, and we could create this kind of a data frame. This contains the same information, and we could do it for even engine location. This engine location column is also a good predictor, as we have found out in the box plot. So the cars with front engine location are 198, which means that there are a lot of cars with front engine location and only 3. So this is kind of this is not a good thing, because in real life scenarios we will be having a lot of cars having rare engine location. So this is a problem. So that is why maybe there were a lot of the difference in the distribution, if we look at this difference in the distribution. So as we concluded in the previous in the section where we were looking at those box plots, that the engine location is a good predictor, but here we could see that this difference in distributions was due to some kind of an anomaly, and we should have more cars with engine location rare to have a generalized model. So this is something we find out after data analysis. This is important because we get very fuzzy and very kind of unexpected results even at test time, and we don't understand it and we get frustrated. So this exploratory data analysis part and exploration part is really important. So then we do this group analysis. And how do we do it? We first of all, as I've already explained in the group analysis in previous videos and other exploratory data analysis videos, that in group analysis we group unique items together and find out their counts and do analysis on those groups separately. So consider this drive wheels containing these 3 different groups, are containing 3 different categories, which is forward, backward, and four-wheeler vehicles. And now what we want to do is we want to group by this data on this drive wheel. So it means on 3 of its categories, and what we want to do is we want to calculate the mean price for each of this group. So for four-wheelers, this is the mean price that we get, and for forward wheels we have this price, and for rear wheels or backward wheels we have this mean price. And this is how we do this group analysis. So we could find out from this analysis that these backward wheels, these rear wheels, are on average the most expensive cars, and then these four-wheel and then front wheels are approximately same in price. Okay, this is how we do this analysis. This group by is very important function, and this is not the only aggregate function. Other than mean, we have a lot of other functions that we could use and do the analysis respectively. Then we group not only based on drive wheels, we also use this body style, and we look at their combinations. So what we could do is that first of all we extract out these 3 columns from our data frame, and then we group by using both of these columns, and then we take the mean inside each of the group. So how many groups do we have? First of all, there are total 3 different categories of drive wheels, and there are about 5 different body styles that we have seen above, and you can find out how many unique body styles do we have. Okay, so it means there are total of, if data contains, then logically there must be 15 groups. Total of 15 groups, but we have total of 12 groups. Why? The reason is that some combinations does not exist in our data. We have only 201 cars, and it is not there are cases where there is even not a single one car having that combination of, for example, this four-wheeler and this convertible. So there is no four-wheeler vehicle in our data set having body style convertible. For that reason we do not have that data set, and there is no four-wheeler vehicle containing this hard top body style. For that reason we do not have that combination. But except for those combinations which we do not have in our data, all the combinations, for example, we have these four-wheeler and hatchback, four-wheeler sedan, four-wheeler and wagon, we have these mean prices. So we extract out the cars having drive wheels category equal to four-wheeler and body style equal to hatchback, and then we take the mean. This is what is happening inside this single line of code. and this is how we get out the price. This group data is much easier to visualize if you want to visualize it when we convert it into pivot table. So pivot table is like an Excel spreadsheet with one variable along the column and another one along the row. So what we will do is we will use this pivot function of the data frame, and we will look at this index, and we are saying that index is four-wheeler and the columns are body style. As I've already explained that these two does not exist. For that reason, we do not have values for these two, for four-wheeler and convertible combination and four-wheeler and hardtop combination. Other than that, we have these values. So we fill these values, these NaN values, basically, which does not exist in our data, with 0. And in visualization part, we will ignore that. So once we have done that, now we have this table, and inside this table, we could see which combination cars with which combination have maximum price. We can see it, but it's much better to visualize it because it takes a lot of more time by extracting out that information. So we use these heat maps, and it's really easy how to create it. You can use this p color method, and you can create also some other methods to create this heat map. And then these x-axis values were created using these x set x text, and these y-axis values were created using this set y text. And this color bar was this color bar function actually creates this side color bar representing the association of color with the value, the intensity of the color and the value. So this whole part is actually covered in our data visualization using Python playlist, in which I have explained different visualizations. Okay, now if you look at this heat map, you can find out that the most expensive cars are the cars with the combination of either rear vehicle and convertible combination, or the cars which are rear vehicle cars and are having hard top body type. So these two are the one of the most expensive cars. And from this heat map, we could see the least expensive car is four vehicle and convertible and four vehicle and hard top. However, these are not the lowest of price, because this 0 actually represent the NaN, as I have filled the values of 0 for NaN values. For that reason, this should not be confused. Instead, we could see what we call the lower value to be in this range. So this is like a skinnish color. So this is the skinnish color. The brighter the skinnish color, the lower the price is, and the lighter the skinnish color, the greater the price is. So the least price is of this combination having this car combination having four vehicles, four-wheel vehicles and four-wheel driving, and this hatchback body style. Okay, so this forward wheel driving and this convertible combination is in between. Okay, so this is how we get it. Now let's come to the correlation and causation. Correlation is kind of as I've already written here, a measure of extent of interdependence between variables, and causation is the relationship between the cause and effect between two variables. So Pearson correlation coefficient is what we have calculated here using this scipy.stats library, and this Pearson R function is used to find out the correlation between wheelbase and price. And this correlation is what we have already explained here. So this has a positive correlation, and this is a negative correlation, and this is a very slight negative correlation, and this is very close to zero correlation. These values that we explain here, these were actually correlations. So how one value varies with the other. So with the if we increase the engine size, the price also increases. This is what we call correlation. But is it the causation? I mean, is it causing the price to increase? I mean, the causation is something different. We'll look at it. We'll look at the difference in detail here. So the Pearson correlation coefficient for different variables with the price is given here. So 0.58, 0.80, 0.69, 0.75, all of these are different correlation values with different wheelbase, horsepower, length, width of these different variables. So price and that variable correlation coefficients are calculated here. But once we have calculated it, so then we could look at these conclusions. So all above continuous features are having positive relationship with price, making them good predictor of price. So if you look at the details, so all of the variables are having less p-value, less than 0.001. It means it is significant. I mean, this is a significance test of p-value significance test. It's not much important for you if you know it. You must know it basically. I'm not expecting my audience to not even know these statistical basic tests. This is basic statistics. However, the lesser it is, the better it is. So then we look at these correlations. So these correlations are very strong, but we should not confuse them with causation. Causation is something different. So it is a cause and effect between two variables. The two variables might have good correlation, but it is possible that one is not causing the other. Causation and correlation is kind of a tricky topic. Correlation calculation is very easy, but causation is difficult to find. Let me give you an example of causation and correlation. So for example, if a person smokes, then the smoking causes the lung cancer. Okay, it makes sense. There is no point of correlation. I mean, however, smoking does not cause the alcoholism in a person. So if a person is alcoholic, it is not caused by the lung cancer. It is not caused by the smoking. However, there is a correlation. I mean, there is a strong correlation usually between people who smokes and people who drinks alcohol. So if a person smokes, it is very possible, it is very likely that he will also drink alcohol. This is one way of saying the correlation. However, the causation is not present here, and the causation is present in the lung cancer part. So this is kind of a tricky thing. I hope so you will understand it. But my point was to make you understand this correlation here. We'll look at this negative correlation. These two are the negative correlation. It means with the increase in these values, the price actually decreases. So it makes sense because it is more efficient if it has more miles per gallon within the city and outside the city. Perfect. So after calculating these correlation and after doing this correlation, after calculating these correlations, then we look at the analysis of variance, which is a statistical method used to test whether there are significant difference between the means of two or more groups. I mean, why do we do that? This is done to find out the important features. If you remember, we looked at the distribution using box plot, and we find out the significant difference in the distribution for different categories of the drive wheels. And using that, we actually concluded that drive wheels is an important predictor of price for different cars in our data set. So this is the same thing, but let's look at it. How do we do it? And I'll explain this ANOVA test final result, and you'll get an intuition of why this drive wheels is a good predictor, and you'll be analyzing in depth this drive wheels feature. So first of all, we will group by our data set using this drive wheels, but we'll be not applying this mean function to aggregate all the prices for a single type of drive wheels. So in the mean function, what we were doing was that we were actually extracting out all the cars having rear wheels category in the drive wheels column, and once we extracted out all the cars, we took the mean of those prices and we reported that when we use this dot mean function. However, in this case, we are not using that dot mean function. Instead, what we are doing is we are getting this group, for example, four-wheeler vehicles, and we are extracting out this price column. So for all the four wheels vehicle, we are extracting out this price column. And if we take a mean of it, it would be same as we looked at it in some minutes before when we were doing this analysis. I just don't want to go there again, but I hope so you understood. You got my point. So taking the mean of all these values will give us the same result as we already calculated when we use this dot mean function alongside this group by function. Okay, I hope so you understand this point. If not, then just go for the documentation of group by and these aggregate functions of dot mean, and you will understand what do I mean here. Okay, so we have extracted out from the data all the cars having this four-wheel property in the drive wheels, and we look at this price, and this column, once extracted out, this thing is also extracted out for forward wheel vehicles and for rear wheel vehicles. And we are having these three different columns or three different array of values for price. These are three different series of values, three different price values for different category of cars, and categories are actually dependent. The categories are actually these drive wheels categories, and we apply this ANOVA test for these three different categories containing these price values. So what it returns is this f value and p value. This f value, greater the f value means the greater this group is, this drive wheel group is, of which we are doing this ANOVA analysis for simple reason, for simple understanding. And this p score is kind of, or this is what we call the test. So it's the lower it is, the better it is. So we have a confidence. This is kind of a confidence score. Okay, now 67.9 makes this this drive wheels a good predictor. But let's go into the depth of it, and instead of using all of these three groups inside this drive wheel category, let's analyze them separately and analyze this forward wheel vehicles and rear wheel vehicles, and then four-wheelers with the rear wheel, and this again four-wheeler with the forward wheels. And we can analyze all the combination and find out which of these combinations are much more important. Then it is possible that maybe this greater 67.9 values is because of any of the two combination instead of using all of the three values. So this is like going into the depth of this column, that which of the category of that feature is more important. And we find out that the ANOVA result, the F value for the first combination, this forward wheel vehicle and rear wheel vehicle, is the greatest. So I mean the whole greater F value for this single column, or for this single feature drive wheels, is because of this combination of forward and rear wheel vehicles. So this shows that these are inside this feature drive wheels, these two groups are the most important ones. So this is why ANOVA is used for. This is what we do with ANOVA for data analysis and for finding out the feature importance and extracting out and engineer the new features. And this is very important for model prediction and model development in machine learning. Okay, then this is what we conclude. After all the exploratory data analysis, we have extracted these continuous numerical variables which were having greater correlation coefficients, and this drive wheels categorical variable, which is also very important. That is what we have analyzed and we have come up with. And the engine size, which in the first stage seemed to be important, is not important. Why? Because of its distribution, because of its uneven distribution of the data set. I mean, we have only three samples from one category and 200 samples from the other category. So so that's why we have to drop that engine size columns. Otherwise, it will create a bias for that specific engine size. Now, once we have done that, then we will use these variables for further model development and evaluation. And this for model development and evaluation is actually done in the playlist of machine learning using different libraries. So there I explain this whole part that I'm going to explain now in very fast forward fashion. In that playlist I've explained in detail using different libraries. Here I'm going to use scikit-learn, and we could use theory create, and I'll be also creating videos on R different packages. So we'll be also creating we'll also be using this R language. Okay, for now we split the data set using this train test split method of scikit-learn. Then we create an instance of linear regression. So this is multiple linear regression that we fit. This model is fitted, and we find out this R squared value by applying this score function and giving this test data, and we get this 0.749. And this is what we have calculated, this function approximation. This is how we have learned the distribution of price. So the red shows this actual value and blue shows these predicted values. We could see the difference here. I mean, this is a very huge difference. I mean, this model is not a very good predictor. We have not learned the distribution quite well. So for that reason, we will learn this polynomial regression, where we want to create features, and those features, extra features, will bring the non-linearity in our model. Instead of linear prediction, linear model fitting for the price data set, we will create non-linear model, and depending on our polynomial feature that we want to use. In this case, once we have inputted the model with 2 degree, so it means this is a quadratic fit. So after fitting it, we test it with the score of 0.86. It seems better, and then once we have plotted it, it looks much better than the linear model. So this blue model is this blue model is kind of a distribution of data set that we have calculated, that we have actually predicted using our model, and this red is the distribution of the price values of actual or data set containing 201 samples. Still, we could see some discrepancies and some problems, but nevertheless it's better than the linear regression. Then we create this random forest regressor, and again we fit the model and we find out the score. It's much better even than polynomial regression, having this R squared value of 0.86. So once we achieve this 0.95 score, then we again look at the distribution, and now we could see this perfect fit for this lower data set, and some discrepancies here, but still it's I'll say a very good fit. we have learned the model. But again, we can refine this model because we have learned the distribution, but we can even refine this model. This refinement is done in the grid manner, where we tune the hyperparameters. These are some of the hyperparameters of the random forest. And in my video, in my playlist Machine Learning from Scratch, I have developed this binary decision tree from scratch, and in that I have explained these different parameters, that how do they affect in fighting this bias and variance. I'm expecting that you know this concept, but I have also explained it in different machine learning playlists. So I'll not be explaining that here, because this playlist is for exploratory data analysis mainly. So we create this grid, and we, inside this grid of values, we find out, we fit this model, and we look at this grid search, and we extract out the best random forest model, and we find out the score for the best random forest model. For better result, we could actually do search for more of the values. So this could be the search should be more and more dense. However, the problem is that the computational expensiveness will be great if we have more and more dense search for hyperparameters. So this is kind of a trade-off between computational efficiency and the hyperparameter search. Once we have done that, we have come up with the best random forest model, which could predict the price after we have extracted the best predictors using our exploratory data analysis. And in the process, you can go on and extract out new features, and again do this model development, and can go beyond 0.95 correlation accuracy.